And hello, welcome back YouTube. Welcome to this discussion on OpenFoam. We are going to continue our little endeavor where we try to plot now instead of just the coarse mesh, but the fine mesh results as well. So this was our little comparison. The orange line is the correlation line, which is based on experimental data. The gray line is the coarse mesh with the correct settings, i.e. to say this is without the round-off error, and the blue line is with a coarse mesh with the round-off error. In terms, you remember the viscosity being excessively high and unrealistic. So that's what we are talking about. Now, next thing I want to take a look at is this, to put in the fine mesh data, which will be over here. All right, fine mesh is here. I will put it here. So I'll just copy and paste these values. So these are the values I want, and this is the area average temperature. Okay, so now okay, cut and paste this over, and now I'm just going to copy this entire thing here and paste it down. Okay, so okay, let me try again. I need the temperature, and yeah, I need to get out the time data. All right, so now it's correct. Why was there error just now? That's because the numbers were incorrect, meaning to say that yeah, the numbers were, let me think, yeah, the numbers were incorrect, meaning to say yeah, I had these two rows were supposed to only take in temperature and heat transfer coefficient data. What I put in was time data, so that's why it kind of gave me a very funny number. So I'm just going to stretch this down, and yeah, there we go. Now you can see the last column will be the correlation Nusselt number. And I'm going to copy and paste all these headers here. Yeah. So yeah. Now we see there's a very good correlation. Okay, so I'm going to put all this data on the graph. Okay, let's do select data. I'm going to add the series name, Nusselt number CFD laminar. Okay, that's the name. X values will be the Rayleigh number, and the Y values will be the Nusselt number. Okay, let's see what the CFD gives us. Coarse, oh right, fine mesh will be it. Yeah, the name was wrong. That's why there was a missing piece. Okay, let's take a look. Try to find this series. Okay. Oh, I got two of the same series. Okay, that explains why. Let me try again. Select data. Okay. Just wanted to check whether the labels were correct. So this is a fine mesh data. Yeah, where the Nusselt number is almost 100. Okay, I should add here series name. This X values will be the Rayleigh number. Y value will be this number. Okay, shucks, I got all my old data pieces cancelled. Okay, try again. Last time. Hopefully it works. I should not use this chart data range. I should use this entries. Okay, back down. Okay. X values, the Rayleigh number. Y value, the Nusselt number. And okay, that should give the correct results. Now we can see oh, this is very frustrating. Why isn't it showing up? Okay, select data, series name, X values, Y values. Ah, there you go. I should have pressed OK instead of cancel. Now you see, okay, this is the correlation, and this is the graph that has been shown. Okay, you can see with the fine mesh values, the Nusselt number is really high, and it's in pretty good agreement with the curve, which is great. I am very happy. Okay, so you see when it's a fine mesh, it agrees very well. Okay, there is some discrepancy, about 10-20%, but that's pretty acceptable. I mean, plus minus 25%. Even the friction factor correlations by the Reynolds number are around that region as well. I mean, generally, if they are in this, they follow the general shape, you should be pretty more or less happy with the results. So this yellow one, it shows the CFD laminar fine mesh, and it matches really well with the Nusselt number with the Rayleigh number. Of course, we can use temperature to sort of give us the same, roughly the same trend. Yeah, roughly the same trend. Excuse me. So that we can see what is the, yeah, instead of it being Rayleigh number dependent, it can be temperature dependent. What do I mean by that? Okay, so Nusselt number in this correlation, it's usually a factor of Rayleigh number and Prandtl number, but both of them are functions of temperature in itself. So Nusselt number is essentially a function of the temperature and the fluid properties. But since the fluid properties have the same function, I mean, this is all diatherm oil, and they have the same polynomial temperature functions that we have before. We can compare Nusselt number to temperature for a very good correlation. So yeah, let's use temperature. Okay, maybe I use paint to explain, it's a bit easier. Maybe I wasn't clear. Alright. So the Nusselt number in the correlation equals some function of Grashof and Rayleigh number. Wait, no. Rayleigh number and Prandtl number, because the Rayleigh number will contain the Grashof number inside. So this is the correlation. Okay, and these both are functions of temperature. Okay, so I'm just going to use a different color. Alright, so if I were to plot a Nusselt number versus a Rayleigh number, I mean, that assumes that the Prandtl number relation is more or less the same. Yeah, this is kind of leaving this variable out. So to make it more complete, because Prandtl number can change with temperature, it's always nicer to compare Nusselt number versus temperature. That while these non-dimensional numbers are very nice, okay, non-dimensional numbers are very nice, we cannot just use Rayleigh number to do it. Of course, the other alternative is to compare Nusselt number against some dimensionless temperature. Okay, I'll shift this baby up. You can compare Nusselt number versus some dimensionless temperature, so that's all normalized. So maybe it's Ts minus T infinity over some initial starting temperature, Ts initial minus T infinity. So this I can just call a theta. So this makes the comparison more standardized throughout. So we can do something like that, and that will show us an even clearer picture of how well these things correlate. Okay, so let's do this. Okay, I'll just get the film temperatures out for this widest correlation. Let me see, T film. Or maybe you just use a TS, because I'm going to use that dimensionless temperature. I'm going to use theta, the dimensionless temperature, which is Ts, surface temperature, minus 300 divided by 500 minus 300. So that's a dimensionless temperature, which I'm using, which is this one. Yeah, Ts minus T infinity minus the Ts over Ts initial minus T infinity. Okay, so that's the theta. I can do the same for that. Okay, so put it here, theta. Okay, now paste it here. Now copy this and paste it here as well. Alright, so now instead of doing this, I can change the parameters as follows. I'll just shift it up. So I compare it versus dimensionless temperature rather than versus some Rayleigh number, which may or may not be consistent throughout. But if you compare with temperature, it's much more fair comparison. So they can take into account the changes in Prandtl number and Rayleigh number all at one go. So that's I'm going to do that. I'm going to do this. Okay. Alright, so now we have a Nusselt number versus temperature, at least the dimensionless temperature. Okay, so it's dimensionless temperature. Alright, we can see the trends are more or less the same. I mean, this is kind of more of a straight line now, and then I mean, this takes into account all the changes with respect to the Prandtl number and everything, but it's more or less the same. So you can see that. Because the only discrepancy is towards the tail end of this line, where you see this sudden dip in convection coefficient, or sudden dip in Nusselt number as compared to this dimensionless temperature. So probably the reason is that, okay, this thing is kind of stopping, it's ending its so-called descent. I mean, that what do I mean by that? Okay, so it's basically like the convection process is almost finished, and there's very little temperature difference to drive any sort of convection flow. So maybe at this point, because I put it I confine it in a box, perhaps that's why it's showing this sort of behavior. But other than that, this curve actually matches pretty well within reasonable, experimental error. It matches this correlation pretty well. I will consider this simulation more or less validated. And since over here you can see the Rayleigh number is below 8 times. Is it? No, it's actually like more than 3 times 10 to the 8th. Okay, so yeah, there is some turbulence we should expect. Okay, for Nusselt number more than 3 times 10 to the 8th. So this effect we can still discuss, but before doing that, of course, I'd like to type out the document for explaining the various situations. So let me open Microsoft Word. So I'm opening Microsoft Word. Hopefully you remember where this all came from. So this was the earliest version of the CosMesh in CosMesh hot-sphere in all case. However, there is some discrepancy because I didn't put in the coefficients right. So why the mismatch? Mesh is too cosh. Okay, so we found now this can contribute, but it's not the only problem. So what do I mean by that? Okay, so remember when we first tried to do this comparison between this CFD CosMesh and this one, we had both the CosMesh was causing an error because once I corrected the rounded off temperature coefficients, it helps to get it closer to the correlation, but not it doesn't go there exactly. Okay, so correlation was so these were some of the plausible things that came out. Correlation, it's developed for steady state, but experiment was transient. Not really, because some experimental data found online with transient conjugate heat transfer was matched the spherical correlation. Okay, so it wasn't because it's transient, so we finished our debugging and this was the result. Okay, I'll put this here. So beta changes with temperature. We don't use bulk fluid temperatures for beta. Yes, we should always use film temperature for property calculation. So this was just updating the old results. Okay, so always use the film temperature. Ts plus T in, okay, let me, Ts Ts plus T infinity divided by 2 for thermodynamic property calculation. Okay, so that's what the same document I this is the same document that I provided last time. So it does cause some things. I mean, it does cause some you should always use the film temperature to calculate. If not, the correlation will never take off, because the Rayleigh, the Prandtl number doesn't change with temperature, which I mean doesn't change with the bulk temperature, which doesn't change itself. I mean, the bulk temperature is constant, so if that's constant, the Prandtl number, if you use bulk temperature as a reference, it will not change as well. So the correct temperature to use is the film temperature rather than the bulk temperature. Okay, so that makes sense for this natural convection. Okay, so we found out that the actual additional reason post debugging is because thermophysical property round off error. So yeah, so okay, let's cancel this. Okay, this one should go on top. Alright. Okay, so the thermophysical property runoff error, it is over here. This was actually pretty serious for viscosity, especially. Okay. So because I rounded off the polynomial, not using enough significant figures for OpenFoam input, so this resulted in mu being several, I think 2 orders of, okay, several orders of magnitude bigger. And also the other thing is that it changes, increases viscosity with temperature. It's not physical for liquids. Okay, so that's the actual reason. So where did we debug? We went to constant oil thermophysical properties, and that actually helps. Okay, so let me expand this. Okay. Using 10 decimal places helps. Okay, so we can see effect of and we can see the effect of just having this average, this corrected of having corrected corrected thermophysical properties Okay. Okay, so you can see the effect of corrected thermophysical properties, without which we get close to 0 Nusselt for convection with fine mesh. All right. So we can see the can see that even with correct thermophysical properties, the fine mesh outperforms the coarse mesh. Okay, so we saw the runoff error actually causes a lot of problems, and with a coarse mesh without runoff error, it was the gray line. Okay, and then with a finer mesh, it actually matches really closely with the correlation. All right, so I'm going to save and put it in a laminar document. Okay, because technically there should be some turbulence. Because the Rayleigh number exceeds 3 times 10 to the 8, at least for the first I think first minute or so, or first 30 seconds at least. Okay, first 30 seconds at least, it should exceed, Rayleigh number should exceed 30. Okay, so now yeah, that's it for the laminar part. We want to see the effects of turbulence as well, and that's the last thing before we can go on to extra like cases, Okay, so I'm going to rename this experimental case as fine mesh sphere oil. Okay, and I'm going to remove the snappy layer at case because that's already done. The non and non-orthogonal experimental case and FV schemes as well. We don't need those anymore. And DI number low. These were all cases to try and debug. So okay, I'll make a directory. Okay, I'll do an all clean first, because if I make the directory and try to shift all these files over, it'll take a very long time. So I just do an all clean. I mean, it's quite nice to see how long this actually takes. Okay. Clock time about 9:565, about 2 to 3 hours. Okay, that's reasonable. All clean. Yeah, should all clean. Okay, I remove the parallel capability. Can do that another time. Or should never mind. I want to remove that. It's just assume it doesn't work. I mean, it doesn't work, so yeah, don't bother. Go to coarse mesh sphere oil. I'll do an all clean here as well. And I'll move both into the hot sphere in oil folder. Move coarse mesh sphere oil into hot sphere in oil. Okay, let's see. Chmod. Okay, so apparently my permissions are denied. So I think you're supposed to chtmod-r 755 the folder name. So it changes the permission. 755 folder name, coarse mesh sphere oil, hot sphere in oil. Okay, so I'm going to move the fine mesh into hot sphere oil. And move the coarse mesh into hot sphere in oil. Ah, man. Let me get that out first. Hot sphere in oil. Clear. Make directory. Yeah, let me skip this part. And fast forward this part. I don't have to see this. Anyway, if you're wondering why the permission was denied, I think it's because I had this VI editor open. Then I could not move coarse mesh sphere oil into the hot sphere in oil. It's not a ch. You don't have to do a chtmod or anything like that. Alright, so what I did is to consolidate these files into a hot sphere in oil directory. Okay, so there's a coarse mesh sphere oil, laminar flow. Of course, that was the corrected version of this coarse mesh folder. Then I also had a fine mesh sphere oil. Okay, fine mesh sphere oil, where we had the corrected results over here. I did a good cleanup of that so that it's not going to cause any problems. Yeah. Okay. So I'm going to make directory results analysis. Okay. So I'm going to chuck the folder here, but first I'm going to git add and upload to GitHub. Okay, so that's it. Next video we want to talk about the effect of turbulence. Insert a little bit of a model to see what changes it makes to this fine mesh version. Okay, so thanks for watching. I'll see you guys again. GitHub link will be in the description. So thanks very much. See you again. Bye.